Hello everyone, my name is Adam Pazske and I'm one of the original authors of PyTorch, although this talk really is on the behalf of the whole PyTorch team and really all of the contributors because it's an open source project. And today I want to present to you PyTorch as a modern platform for machine learning research and production. So if I were to describe essentially what PyTorch is using just like one sentence, I would say that PyTorch is NumPy with batteries included. And especially some of those batteries are crucial when it comes to executing certain kinds of workloads, so in particular machine learning. Those batteries, right, those features include things like accelerator support, so you can easily write your code, your ND array code, which essentially not only can execute on the CPU as it would normally with NumPy, but it can also use GPUs or TPUs or any other accelerator that might become popular in the future. Also, another really important feature is high-performance automatic differentiation. Basically what it does is you only have to write basically like your complicated machine learning model, and the code to compute the gradient of, let's say, some loss function can be derived by the system automatically for you without you having to sit down and actually do the derivation by hand and later implement it in code again, which is obviously very error prone. More importantly, I guess for this conference, the features we will be covering right now are a just-in-time optimizing compiler for ND array code, which also supports code export such that it can actually execute entirely without Python, and also a distributed computing library for PyTorch. So a bit of a origin story of PyTorch is that it actually came from Facebook AI research, and as such, sort of research has always been this driving factor in how we were designing and how we were thinking about the library, right? We were always sort of striving to make it as flexible as we can, and I would say that in research we did a pretty good job. If you look at the implementations of the latest machine learning papers, then in the last quarter, over half of them were actually implemented in PyTorch. So that is more implementations in PyTorch than in all the other sort of libraries combined, which I think is extremely exciting. But ultimately, we sort of had this, we started with research, but research is not everything, right? A lot of this research is done to produce models that are supposed to interact with real world, right? Like you can think of autonomous driving cars as one example. And industry and deployment and actually interacting with the real world is not an area where we did great in the past, I would have to say, but it was really our focus for the past 2 years, and hopefully, as you'll see, we are sort of really achieving a lot in that regard. So when I'm talking about deployment, there are really two use cases I think that are somewhat different, and that even includes training, right? One is embedded devices, where essentially those are often battery powered, and you really want to run with maximal efficiency, with no sort of cycles wasted on jobs which you would normally have to do, such as executing Python, right? So regular ways to use PyTorch, which is just writing Python scripts, that doesn't really scale for those embedded devices. And so we had to come up with a solution for that. On the other end of the spectrum, you have computing at scale, right? So you might be deploying your machine learning solution to a whole fleet of servers, or you might be running essentially large-scale distributed training, which is very popular these days, right? Like previously, people would be training a single network on a single GPU for a few weeks, and now on the same data sets, people can actually, using obviously whole clusters, they can basically train those networks to similar accuracy within seconds or sometimes minutes. So the question is, okay, so we started with this PyTorch Eager is what we call this NumPy-like mode, which doesn't really scale properly to both of those, scale up nor down to both of those deployment scenarios. So our solution to this was to create PyTorch Script. And PyTorch Script essentially is a whole new programming language. The only different, but you shouldn't really be afraid of that, because the new programming language essentially is Python for the large part, so it uses exactly the same syntax, and every torch script function is essentially a valid Python function, and it is exactly the same function. It computes exactly the same thing every time you call it. The only caveat is that it is not all of Python, right? So there are some restrictions. Python is extremely dynamic, and because of this, for example, the Python interpreter is incredibly complex. So we had to actually restrict it in some ways to actually make it more optimizable. So we can do more advanced static analysis on our code, and we can actually, let's say, rewrite certain patterns to make them faster or numerically stable. The other benefit we get from that is that it becomes exportable such that it runs entirely without the Python interpreter, and we can just use our own lightweight interpreter, as I've mentioned, because the language is so much simpler than the regular Python. But also caveat here is that, it is a restriction, but it is a pretty expressive restriction. So really most of the models that I've seen that are written in PyTorch easily fit within the realm of Torch Script, and you should be able to convert those relatively easily. So just to give you an idea of how such a conversion looks like, the code in here is not super relevant, but the general idea is that this is a part of the implementation of a recurrent neural network that you could find in some PyTorch examples. And so there are really two steps you have to do to convert your function to Torch Script. One is you have to add argument type annotations. This is because Torch Script is actually strongly typed, and so it will check that you're not overriding a variable with a value of a different type. But annotating arguments is actually sufficient. The rest of the body can be handled using type inference, and so with this limited set of annotations, it's actually sufficient for us. Also, this is obviously also a benefit for documentation of your code, where callers of those functions will at least know what they should be passing in. And then another thing to do is this small annotation here at the top that says PyTorch Script, and basically what it does is when Python gets there, when it actually sort of creates the function, whenever you put Torch Script, instead of creating a regular Python function, this annotation will look at its source and it will try to verify if the source actually fits in the subset that we decided to that we can actually support in Torch Script, right? If it does, then everything's all right. And your program functions exactly the same. There's really no observable difference. It should give you exactly the same outputs, no matter whether you have this annotation or you don't. The only difference is that every time you call this function, it doesn't go through the regular Python interpreter. It actually goes through this optimized path, which can do really interesting rewrites, as well as sometimes even code generation at runtime to really sort of produce something very tailored to your particular workload, right? Now the other alternative is that whenever you put this annotation, something fails. You get an error, and whenever you get an error, this basically means that something inside this function does not really fit into the subset of Torch Script, and the error should basically point you exactly to the place where that happens, and basically explain you why that is and how you should be able to fix it. So you can see that hopefully this should be relatively straightforward, and as you can see, that should already give us a relatively good path to embedded deployment, right? The workflow goes like this. You write a PyTorch model using regular PyTorch eager, you sort of iterate over it, right? The researches are often significantly different from deployment in that in research you really want a lot of flexibility because you will be iterating on the model, right? And deployment usually is taking the sort of result of this particular, of the final iteration and actually putting it into some environment, except, at this point it should really run as efficiently as possible. And so you write your PyTorch model using PyTorch eager, you iterate on it as long as you want. Once you're done, you just add those Torch Script annotations in a few places in your code, and then using Torch save, you can actually emit like a self-contained package that contains both all of the parameters and all of the state of the model and of the sort of code that is there, along with the serialized code, right? And once you have this package, there are ready-made libraries available on both Maven and CocoaPods for Android and iOS respectively, which you can sort of easily link into your mobile app, and they will be able to actually interpret those packages such that you can easily generate predictions from those models, or even in the future train them. And those packages are really lightweight. It's essentially like just, let's say 5 megabytes, and that's sort of all the weight it actually adds. All right, so let's move sort of to more of a theme of this conference, which is actually working at scale. So when it comes to deployment, one thing we were really missing, I think, in the past is like a sort of good out-of-the-box deployment solution for web. Now we actually have PyTorch Serve. So that is an official project which exposes, essentially can take those packages that either Torch Script produces or because it runs on like a regular computer, it can also take eager models, in which case it will use Python to, actually serve those models. But the nice thing about it is basically for the common tasks, like object classification, you basically get like a nice REST API, which semantically makes sense for a particular task and for a particular domain. And you can easily sort of, basically in minutes, you can get up and running and serving your model to the web, right? And it also supports some interesting features. Like, for example, a lot of those models are more efficient if you evaluate them on multiple inputs at once, right? But usually for every single user, you will only be getting a single input. right? So what PyTorch Serve can do for you is it can batch requests. So whenever requests are coming, it can sort of delay them until like a finite time horizon, like a short time horizon, and it can try to like accumulate a few of those in that amount of time, and it will try to evaluate the model on all of those inputs at the same time to better make use of your hardware. All right, so that was like the main thing for when it comes to deployment. I think that was like the main sort of advancement we did. Now let's focus more on the actual like large-scale training. So since version 0.2, that was a really long time ago. Sort of the main way to actually do distributed training in PyTorch was to use an MPI-like multi-controller model. So the idea is that you write a single Python script, you launch it on a lot of different hosts, and all of those hosts sort of evaluate the script as they go, and sometimes they reach something called a collective operation, which is essentially like some data exchange between some of those hosts. And those include like most MPI sort of collectives you might know from different MPI implementations, like broadcast, all reduces, gathers, scatters, point-to-point communication using send and receive as well. And that seemed to work out pretty okay. The only problem with a lot of those MPI-like interfaces is that, well, they lack fault tolerance. And fault tolerance is really important once you really want to scale up, right? So we did a lot of changes in the distributed backend, and that led to PyTorch Elastic. So PyTorch Elastic is exactly this like wrapper around your MPI-like job, which utilizes a Kubernetes cluster. You can either get one on premise, or you can basically rent those from any of the cloud providers. And what it gives you is it provides you fault tolerance. So anytime any part of the job fails, it will restart it automatically from like a well-known state without sort of reconstructing the whole system from scratch. And also another really cool thing, I think, is dynamic capacity management. So you can, for example, use on-spot instances, and whenever they become cheaper, you can actually scale up your training, and whenever they become more expensive, you can actually scale it down without sort of aborting the whole job and restarting it periodically, right? Which I think is also really nice. And also, in case those instances sort of get taken away from you, everything's handled for you automatically as well. All right, so getting back to how you express those jobs, though, in version 1.5, which is the latest release, there's actually a super exciting thing, which I would call a single controller model for distributed. So the difference now is, unlike in the multi-controller model, well, you have a lot of those like scripts which sort of have this distributed control and like sometimes will decide to communicate. Now there's only one Python script actually executing the code, and sort of the rest of the hosts just become sort of dumb workers which await commands from this single controller script. So obviously there are some problems with that, like this single host might become a little bit of a bottleneck for the system. But assuming you can actually like slice off chunks of works that are large enough, such that this single machine might still be enough just to like saturate still a fair amount of hosts. And the API itself is really simple, I would say. It's really just 3 functions and 1 class. Basically what those do is, again, really simple. RPC Sync, you give it a worker name, so that is the host on which, or the process in which the particular computation will be evaluated. You give it a function to evaluate, and you give it arguments. And what RPC Sync does is it will take the arguments, it will ship them to that worker, it will compute the function, it will get the result, it will ship it back to you, and once it gets back to you, it will return the result, right? So it's blocking, this is why it's synchronous. Then there's RPC Icing, so that is very similar. It's just that once it ships the arguments and computes the function, it returns immediately. It doesn't wait until the data comes to you, but the data will come to you automatically as well. The only difference is that RPC Async actually returns something called a future object, which essentially you can use to like wait on the result of this job and actually get it once it arrives to you, right? But you can, for example, use it to like dispatch a bunch of those jobs and then wait for the results to come in. More excitingly, I think, the last 2 things are really much more interesting. So remote is, again, very similar to RPC Async. The only difference is that, it obviously executes asynchronously, but it also does not imply that the result will ever actually come back to the controller program. Instead, what it returns to you is a remote reference object. And those remote references are really, really interesting because they can also be passed around as, as regular objects, as arguments to other functions as well. And so what this means is that you don't sort of have this implicit data transfers, right, to the control program, and from the control program, you can just whenever some function finishes on some worker, it will just store its result, and it will store its result as long as like any of the hosts in the host system contains a reference to that particular object, but the reference to this object can be shared, right? And for example, method calls on this object will become sort of tasks to be queued on the worker which actually manages that particular object. So some use cases for this particular scenario are pipeline parallelism, right? If you can easily, using this remote reference, you can chain different tasks, and sort of you can by passing those remote references, you can make it easy to actually like build very complex sort of communication structures between different tasks in those pipelines. Also model partitioning. If your model does not fit onto a single computer or on a single device, you can easily like launch a bunch of processes. With this API, you basically write as if you were writing programming a single process, but now different parts of your model actually do the computation on different parts on different hosts. Then asynchronous parameter servers. This and reinforcement learning example actually makes use of a very interesting feature of remote references, in that you can actually create remote references yourself to the objects that are in your controller program. And once you create those references, you can also pass them on to other workers. And what this basically means is that those workers get a means to asynchronously call back to your controller program, for example, inform it about some progress, right? Or ask it about like the next actions to be done. And I actually have an example for reinforcement learning that makes use of that. So often in reinforcement learning, right, you have some agent and you want to train it to like make wise decisions about which action to choose in what circumstance. And you want the agent to basically interact with a lot of different environments, but maybe if the environments are somewhat expensive to simulate, you might want to like distribute the simulation over multiple different environments, over multiple hosts, right? So the way you write it in a single controller program, and again, like all of the code that you see here essentially lives in a single file. It's just the distribution, sort of the code that like actually that actually queues those functions, which will distribute the computation. So we have an implementation of the agent, right, which is a class with two methods: select action and receive reward, to sort of better inform the future choice of actions. And then, so at the bottom in the controller half, what you can see is that in the controller, we will essentially create the agent, we will launch a bunch of those experiments using the async call, and we will pass a remote reference to the agent to every single one of those workers, right? And then we will basically wait until all of those experiments complete. At the same time, workers, so this def run experiment is still, of course, in the single program. It's just that it will actually be executed on those workers, right? Because we sort of passed it to RPC async. What each one of those workers will do is it will basically loop until the simulation is not complete, and as long as it is not, it will ask the agent, which lives in the controller program. So this is this asynchronous callback for the next action. It will simulate a step of the environment, and it will inform the agent about the reward. So this way you can easily, for example, create agents which interact with lots of environments sort of at the same time in a distributed fashion using basically a really tiny script, which I'm super excited about. Then finally, this is a bit more of a backend change. We're also sort of working on overhauling the backend for this particular single controller mode, right? The difference now is that previously we were sort of leaning on a lot of libraries that were designed for this collective communication, but this single controller model sort of makes more use of like a point-to-point communication. So TensorPipe is a new backend that optimizes point-to-point communication and also adds a lot of interesting features. Like it is topology aware. If a few of your processes are on the same host, it will not go through the network interface. It will just like use shared memory to exchange the data. It no longer requires full meshes, so that is better for fault tolerance. Whenever anything drops out, you don't sort of lose your whole network. A large part of your network sort of can stay untouched. And it also supports structured messages, right? So you can not only send like unstructured buffers of data, now you can also like ship, let's say, dictionaries with some tensors and some metadata that will explain you how to interpret them whenever the receiver gets them. So that is everything sort of when it comes to distributed updates, I think, in PyTorch. Just to close off, I wanted to share a few success stories, just to show you that we're not only doing good with research right now, we're also sort of getting increasingly a bigger foothold in the industry as well. So I have 4 stories to share with you right now. One on the left, you have Mars. Mars is a company that produces a lot of the well-known suites, and they're, for example, using PyTorch to do quality assurance as part of their production processes. Then a lot of the self-driving car companies actually also use PyTorch, and that group includes companies like Tesla. Then you can have in engineering you have Autodesk, so the makers of some very popular CAD software packages. They're actually using PyTorch to also sort of do semantic search for some parts that might be relevant in certain contexts. And finally, when it comes to translation, Duolingo, which is an application that you can use to learn foreign languages, they actually use PyTorch to sort of tailor the experience, tailor the courses to everyone, every single user individually. Just to finish off, some interesting statistics as a sort of health check on the project. Right now we have over 39,000 stars on GitHub, and we have over 1,400 contributors. Of course, we're extremely grateful to every single person there. We also have very active user forums. If you have any issue, you can just go there, and some very experienced members of the community will surely help you, no matter how simple or complicated your problem is. Those forums actually get like over 3 million monthly views. And if you count like all of the downloads from the official distribution channels for the package, that amounts for over 10 million downloads since the beginning. All right, so that is everything I have prepared for today. Thanks a lot for listening, and I hope you've enjoyed it.